On July 15, 2025, humanity received a message from the depths of cosmic history. A signal not in words, but in light, traveling for billions of years across the vast, silent expanse of space. It was a moment that would ignite the imagination of scientists and stargazers alike, a reminder that the universe still holds secrets waiting to be uncovered. This message wasn't from distant civilizations or extraterrestrial life, but from the universe itself, a cosmic echo from an era when the first galaxies were just beginning to form. It was as if the universe had whispered a secret, one that had traveled eons to reach us. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, captured the ancient light of an object so strange and powerful, it sent ripples through the scientific community. This wasn't just another distant star or a faraway galaxy, it was something far more mysterious, an anomaly that defied our expectations. What Webb found was a candidate for a direct collapse black hole, a theoretical giant, never before seen, thought to be the missing link in our understanding of how the universe's most massive black holes came to be. Unlike the black holes formed from dying stars, this one seemed to have emerged fully grown, bypassing the usual cosmic steps. Its discovery challenges everything we thought we knew about the birth of black holes and the evolution of galaxies. Scientists around the world are now re-examining their theories, questioning whether our cosmic origin story is far more complex and more fascinating than we ever imagined. The object appears impossibly massive for its age, like stumbling upon a towering oak tree in a field where only tiny seeds should exist. Its very presence in the early universe is a puzzle, hinting at unknown processes that could have shaped the cosmos in ways we're only beginning to grasp. This single, brilliant point of light could force us to rewrite the first chapter of galactic history. It stands as a beacon from a time when the universe was young, challenging us to look deeper and ask new questions about our place in the cosmos. The journey to understand this cosmic enigma is just beginning. As scientists prepare for new observations and develop fresh theories, we stand on the edge of discovery, ready to reshape our view of the universe and perhaps our own origins forever. To grasp this discovery, we must appreciate the James Webb Space Telescope, our most powerful eye on the universe. Launched in 2021, JWST is a time machine, capturing light that's traveled over 13 billion years. Unlike Hubble, JWST specializes in infrared, revealing ancient redshifted light invisible to other telescopes. Its giant golden mirror peers through cosmic dust, exposing the hidden nurseries of stars and the earliest galaxies. Since becoming operational, JWST has shattered records, revealing a universe more complex than we imagined. The Cosmos Web Survey, mapping the early universe in unprecedented detail, led to the discovery of the anomalous signal. JWST isn't just confirming what we know, it's built to find what we never dreamed possible. Traditionally, black holes are born from the spectacular deaths of massive stars, those with at least 20 times the mass of our Sun. These cosmic giants burn through their fuel at a furious pace, shining brilliantly for millions of years before reaching their dramatic end. When these stars finally exhaust their nuclear fuel, gravity takes over in a violent collapse. The core implodes, triggering a supernova explosion that briefly outshines entire galaxies. What's left behind is a black hole, a region of space so dense not even light can escape its grasp. Over billions of years, these stellar mass black holes can merge with others or feed on surrounding gas and dust, slowly growing larger. Through countless cosmic collisions and steady accretion, they gradually transform into the supermassive black holes we find at the centers of galaxies. But there's a puzzling problem. Astronomers have discovered supermassive black holes in the early universe, existing just a few 100 million years after the Big Bang. These giants appear far sooner than this slow step-by-step process should allow. It's like walking into a kitchen and finding a towering, perfectly baked cake just minutes after the ingredients have arrived, before anyone's even had time to mix the batter. Even the most optimistic models of black hole growth can't explain how these cosmic behemoths manage to form and grow so quickly. The numbers just don't add up, leaving scientists scratching their heads and rethinking what they know. It's as if the standard recipe for making black holes is missing a crucial step. Or perhaps there's an entirely different recipe we haven't discovered yet, one that could explain this cosmic mystery. This enigma has kept astronomers searching for answers, pushing the boundaries of our understanding and inspiring new theories about the origins of the universe's most mysterious objects. Enter the direct collapse black hole, a radical solution to the timing problem that has puzzled astronomers for decades. The universe's earliest supermassive black holes seem to appear far too quickly after the Big Bang, leaving scientists searching for a way to explain their rapid growth. Traditional black holes, born from the deaths of massive stars, simply couldn't have grown large enough, fast enough, to match what telescopes have observed in the ancient cosmos. Instead of forming from a dead star, a DCBH forms when a massive, pristine gas cloud, untouched by previous generations of stars, collapses directly under its own gravity. These clouds are made almost entirely of hydrogen and helium, the simplest elements, left over from the Big Bang itself. With no heavy elements to cool the gas and trigger star formation, the entire cloud can remain intact, setting the stage for something extraordinary. In the early universe, these clouds, sometimes hundreds of thousands or even millions of times the mass of our Sun, could avoid fragmenting into stars if bathed in intense ultraviolet radiation from nearby galaxies or clusters of young stars. This radiation acts like a cosmic shield, preventing the gas from cooling and breaking apart, and allowing the whole cloud to collapse as one. The result? The entire cloud collapses at once, bypassing the usual steps of star birth and death and creating a black hole born big, 100,000 solar masses or more, right from the start. This is a cosmic shortcut, allowing black holes to leapfrog the slow process of stellar evolution. This enormous head start could explain the rapid appearance of supermassive black holes in the early universe, helping to solve one of astronomy's greatest mysteries. With such a massive beginning, these black holes could quickly grow even larger by swallowing up gas, dust, and even entire stars. DCBHs are a different species altogether, possible only in the universe's earliest, simplest days, before galaxies and stars had fully taken shape. They represent a unique window into a time when the cosmos was still young and unpolluted by heavier elements. Until now, these direct collapse black holes were purely theoretical, predicted to shine brightly as they devour matter, but lacking the chemical fingerprints that come from star formation. Their existence has been a tantalizing possibility, waiting for evidence. Finding one would be like discovering a dinosaur born fully grown, a cosmic anomaly that could rewrite our understanding of how the universe's most massive objects came to be. The discovery began with careful analysis of Cosmos Webb data by Peter van Dokkum's team. Amid countless faint galaxies, one object stood out, exceptionally bright, from a time when the universe was less than 1 billion years old. Previous telescopes missed it, but JWST's infrared vision made it clear. Its spectrum lacked the heavy elements expected from star-filled galaxies. Instead, it matched predictions for a direct collapse black hole. The object was compact, luminous, and seemingly devoid of stars, a near-perfect match for theory. The team announced their findings, stressing it's still a candidate pending further review. Yet the evidence is compelling, igniting excitement and debate worldwide. This could be the first tangible proof of a decades-old cosmic theory. This discovery is the latest blow to the standard lambda-CDM cosmological model. JWST has already found galaxies in the early universe that are too massive and mature for their age. The direct collapse black hole candidate offers a physical mechanism for this rapid growth, massive black holes acting as seeds for early galaxies. It connects two major puzzles: the speed of galaxy formation and the existence of supermassive black holes. Science advances by confronting evidence that challenges old models. JWST is stress-testing our understanding, forcing us to consider that our theories of gravity, dark matter, or cosmic origins may be incomplete. As John Mather says, this is not a crisis, but an opportunity to follow the evidence wherever it leads. If confirmed, direct collapse black holes will rewrite astronomy textbooks and reshape our understanding of galaxy formation. Students will learn that black holes can be born two ways, from dying stars or directly from primordial gas. This discovery opens a new field of inquiry, driving astronomers to hunt for more DCB8s and develop new technologies. It strengthens the case for investing in ambitious science, showing the value of curiosity-driven exploration. Such breakthroughs inspire the public, spark wonder, and encourage young people to pursue science. They remind us that exploration is essential to the human spirit. In a divided world, the quest to understand the universe unites us all. The scientific community has responded with both excitement and skepticism, hallmarks of the scientific method. Peter van Dokkum's team is planning follow-up observations to confirm the object's true nature. John Mather emphasizes that JWST was built to challenge assumptions and find the unexpected. Other astronomers are exploring alternative explanations, from unusual star clusters to hidden quasars. This rigorous debate is what gives science its power and reliability. Whether this object is a DCBH or something entirely new, it's already taught us the early universe was full of surprises. Our quest to understand it has only just begun. Why does a faint smudge of ancient light matter? Because it reshapes our cosmic story and our sense of belonging. The universe may have built its giants in ways we never imagined, deepening our understanding of our origins. Discoveries like this drive innovation, inspire wonder, and remind us of the value of curiosity. The scientific method, observation, theory, debate, and verification, guides us closer to truth. Science is not static. It's a dynamic, self-correcting journey. The story of this black hole is a story of wonder and humility. The universe is still full of mysteries, inviting us to keep exploring. The message from the dawn of time is clear: there is always more to discover.